Hello everyone, my name is Joseph Lineberry, and my research topic for today is how we can surpass the limits of traditional computing using quantum mechanics. It's a big topic, so let's get started. Traditional computers get more efficient by increasing the density of their transistors on their circuit boards. This follows a exponential pattern, which is called Moore's Law, which states that every year or two, the number of transistors per square inch on a circuit board will double. Transistors work by controlling the flow of electrons throughout a circuit. The current transistors are so small they're nanometers thick, which are smaller than wavelengths of visible light. And at such small scales, the electrons that run the circuits actually can do something called quantum tunneling, which completely disrupts the circuit. Quantum tunneling occurs when an electron, or other small particles, can bridge a gap that would otherwise not be able to pass. So if this happens in a normal computer, a 0 could become a 1, which would throw out all of the data that it's processing. So quantum computers can get around that because they aren't working with electrons at such a small scale. Superposition is when a particle's characteristics aren't confirmed, such as their spin, which, when it's not defined in such a way, it means that they can be both possible answers at once. They aren't set as one until they're determined. Entanglement is when multiple particles are bonded together such that when you measure one, it tells you what the other one also is, no matter the distance or when you do it. Qubits are the quantum bits of a quantum computer. Whereas traditional bits can either be a 1 or a 0, they can only be two possible choices. Qubits can be any possible combination of 0 and 1. Running a qubit through a special logic gate will collapse them into one specific identity, but qubits can be programmed to have a higher chance to be a 0 or a 1 depending on what they're needed. So you could have 70% 0 and 30% 1, so you'd have a 70% chance of being a 0. Quantum computers can outperform traditional computers in that they can do multiple simultaneous processes at once. A traditional computer can run through a single line of code at once, and it can do many of those in a second, but it can only do one at a time. A quantum computer can run hundreds at once, which vastly increases the amount of data it can process. So something that would take a traditional computer years and decades to crack can be done in days on a quantum computer. This includes information privacy, which is done by multiplying two extremely large prime numbers together, and it makes such a big number that it can't be hacked by a normal computer unless you spent decades running it, whereas a quantum computer could run the calculations on that and find out in hours what the information is and get into your security network. Currently, some of the current models of quantum computers include D-Waves, which uses quantum annealing, which is where they link qubits up to a magnetic field so that they can solve optimization problems, where you have different points on a map and you try to figure out the most optimal way of going from one point to the next and fulfilling all of them at once. Their largest model currently has over 2,000 qubits linked together. IBM, on the other hand, uses more universal qubits that can solve most traditional problems that you would think of, but they can only get up to 50 qubits at a time, and they can only run them for 90 microseconds. But those are both industry records for that, because it's so difficult to house a qubit, because you need to keep it at near 0 degrees Kelvin and it's incredibly expensive to run. Quantum computers are very expensive and they require large infrastructure that makes it very difficult to house. So it's not a direct comparison to standard computers, which can fit in your pocket like in your phones. But for large operations, such as big corporations or companies that want to do massive calculations, it's a step above normal computers. There's still a lot of research to be done on it, as they're a lot younger than traditional computers, which have been around for over 100 years now. But in time, will go on to supplant traditional computers for many problems.